So we talked about just a quick recap. You had orbitals, and those orbitals would pull each other's electrons, and the electrons would start overlapping. So that was the formation of sigma bonds. And then what would happen is that those sigma bonds came in different shape and sizes, an S and P orbital overlapping, the electrons merging up and forming a covalent bond. There was a P and P overlap. So there were all types of sigma bonds, and then we studied about pi bonds, which was over here. That in pi bonds, what would happen was that the atoms would be bonding together. They would first form a sigma bond. Electrons would overlap, but they would have other orbitals that needed electrons that were half filled. They were not completely full. So they would also start overlapping. And those other orbitals were parallel to each other. There was an end-to-end overlap, which was a sigma bond. And then there was orbitals lying in parallel to each other, and they would form pi bonds. Electron density was lying above and below the axis. Similarly, you had triple bonds. In triple bonds, you had a sigma bond that was formed initially. Then you had a orbital that were parallel to each other. They would form a pi bond. There would be another orbital parallel to each other on a different axis, z-axis, and they would also start overlapping in front and behind. So that was like that was basically what a triple bond was. And we talked about hybridization. We talked about whenever atoms bond, the orbitals, they change shape. Electrons get pulled in different directions. So the orbitals or the region where you find the electron, that's going to be different now. So tetrahedral was when sp3 hybridization was when carbon would form bonds with 4 different atoms. And you had sp2 hybridization. In sp2 hybridization, you had carbon forming bonds with just 3 atoms. So electron density got attracted in 3 different directions, and the 4th electron would end up forming a pi bond. And similarly, you had sp hybridization. In sp hybridization, I told you that carbon was only bonded to 2 atoms. So 1 electron went this way, one of the electrons went this way, and there were 2 orbitals that were left, and they would end up forming pi bonds. So that was sp hybridization, and we did all of that. Now there's a thing called shapes of molecules. So let's quickly try and do shapes of molecules. Just let me add pages first. So shapes. I said now shapes of molecules. And what determines the shape of a molecule? There's a theory called valence shell electron pair repulsion theory. Which is also for short, it's known as VSEPR. So now it's kind of a simple theory, that is that every atom has bonds around it. So for example, the first shape of a molecule is that it's a linear shape. If there are 2 bonding pairs of electrons. So if you have a bunch of bonds around an atom, like a carbon dioxide molecule, it's got a double bond on one side, and it's got a double bond on the other side as well. What the theory simply states is that the electrons over here are going to repel the electrons on the other side. So they're going to be as far away from each other as possible. So the bonded electrons over here and the bonded electrons over here are going to stay as far away from each other as possible. Electrons over here repel electrons over here. So the only way that's possible is that the angle between them is going to be 180 degrees. And the molecule is going to be completely linear. So that's the simple idea of what this theory means. That electrons in the outer shell, bonded electrons in the outer shell, they repel other bonds that the atom is forming. And the shape is determined always by the central atom. It's always the central atom that you have to look at, how many bonds it's forming. So if there are two bonding pairs, there's a bond over here, there's a bond over here, then the shape is going to be linear. And the angle is going to be 180 degrees. There are other examples as well. For example, you have an HCN molecule. Now in an HCN molecule, the same thing happens. There's a triple bond over here. There's a bunch of electrons over here, and there's a bunch of electrons being shared over here. Both these electrons are going to repel. So if the triple bond is on this side, then the single bond over here is going to be completely on the opposite side of this carbon atom. Okay, is this clear? Maryam, is this clear? Abdullah, is this clear? Aisha? Anna, is this clear?
Yes, sir.
Yes, sir.
So whenever you see an atom making or having just two pairs of bonds, remember, think of the double bond as one thing. Think of the triple bond as one thing. So there's a pair. So there are pairs of electrons over here. There's a pair. There's bonded electrons over here, and they're going to repel each other. The next shape is shape number 2. That is when you have 3 bonding pairs. So when an atom has 3 bonding pairs, like an AlCl3 molecule, so the shape is going to be fan shaped. There's going to be one bond over here, one on this side, one on this side. So for example, Al bonds with 3 Cls. So again, the theory suggests that the bonded electrons over here and the bonded electrons over here, they're going to repel each other. Just like the blades of a fan, imagine them repelling each other. So the only possible way that they can be as far away from each other as possible is that if the angle is 120 degrees, and that's called fan shaped. The name of the shape, which we are calling fan shape, that's actually trigonal. It's known as a trigonal planar shape. And it's a flat two-dimensional shape. Like if you look at any fan, it's completely flat. It's a two-dimensional shape that's known as trigonal planar. So that's one. But there's a variation for this as well. Sometimes what would happen is, so I'm going to call this A. Sometimes what would happen is that an atom, the central atom, you can remember, focus on the central atom and how many bonds it's making. So sometimes what would happen is that the central atom is having one lone pair and it's got 2 bond pairs. What that basically means is that instead of having a bond on one side, it actually has electrons, but those electrons are not involved in bonding. So a lot of times atoms have lone pairs. Lone pairs are those atoms in the outer shell that are not involved in bonding. So one example is, if you look at a sulfur molecule has 6 electrons. It makes a double bond with oxygen in SO2. It makes another double bond with another oxygen. And on the third side, there are electrons, but those electrons are not really doing anything. That's known as a lone pair. So what a lone pair is, they are the unbonded electrons in the outer shell. So not all electrons are involved in bonding. For example, if I draw an HCl molecule, in an HCl molecule, you've got an H and you have a Cl. The Cl has 7 electrons. So that's 1, 2, 3, 4, 5, 6, and 7. The H only has 1 electron. Now, what happens in the bonding is that Cl needs 1 electron, so one of the electrons of H gets pulled towards this Cl. But you can see that for Cl, not all of the electrons are involved in bonding. It's got these electrons over here, and these electrons over here. Not all of them are involved in bonding, so it's got 3 lone pairs. So it's got 3 pairs of electrons that are not doing anything. The way you show them is that there's an HCl molecule plus this Cl is going to have a total of 3 lone pairs. Okay, so lone pairs are those outer shell electrons that are not doing or that are not involved in bonding. So sulfur dioxide over here, it's got 2 electrons bonded over here. It's got 2 electrons bonded over here. And out of the 6, it still has 2 electrons remaining in its outer shell. So in total, there are 3 electron densities or 3 pairs of electrons. A pair of electron over here, bonded pairs of electrons over here, and it's got a bunch of electrons over here. Now the shape is pretty similar. It is fan shaped. It is like a fan, except that there's no atom bonded to the top. I mean, there's nothing on the top. So imagine it's still fan shaped, but with one blade of the fan missing because there's nothing on top. I mean, it's just a bunch of electrons. There's no atom attached to it. Is the shape clear, this one? Yes or no?
Yes, sir.
Nabila, is this clear? Hania, is this clear? Zahib, Mahat?
Yes, sir.
Okay. So imagine a fan with one blade missing because it's got electrons here, which are repelling these electrons, and the electrons over here are repelling these electrons. So it's kind of the same shape, except there's no atom attached over here. So the shape is referred to as a nonlinear shape. It's not fan shaped. Like you wouldn't call a fan with one blade missing a fan. So the shape is known as a nonlinear shape. It's going to look like this. It's basically this and this. The top is missing. I mean, the third part is missing. There's nothing there. So it's nonlinear. Nonlinear means that it's a bent shape, or you can call it nonlinear, or you could call it bent. And the angle would pretty much be the same. But in this case, it would be between 117 to 120. I mean, it would be almost the same, except remember one thing, that bonded electrons are further away because oxygen over here is pulling the electrons. So these bonded electrons are kind of further away from the atom. The lone pairs are really close to the atom. So the lone pairs always exert more repulsion. So make sure you know this, that whenever you have a lone pair, like if you have all these bunch of electrons, these electrons over here would be further away from Cl because the H atom over here would be pulling on those electrons. The other electrons would be a lot closer to Cl. So the same is the case with sulfur. These electrons over here belong to sulfur. There are a lot, no one is stealing or trying to pull those electrons away from it. The electrons that sulfur is sharing with oxygen over here, they're kind of further away because oxygen is trying to pull those electrons, and this oxygen is also trying to pull those electrons. So it's a non-linear shape, bent, and lone pairs exert more repulsion. Why? Because they are closer to the atom. And because of the greater repulsion, more repulsion would be exerted. So the double bonds would be kind of slightly closer to, they're going to be slightly closer to each other. So instead of making an angle of 120 over here, all the bonds are exactly the same. Imagine if there's a lone pair on top, these bonds over here and these bonds over here, they would be just very, very slightly closer to each other. So the angle would by just a very tiny amount, it would decrease from 120 to, it might be somewhere between 117 and 120. So is this clear?
Yes, sir.
Yes, sir.
Yes, sir.
So whenever you see an atom having 3 bonded pairs, the angle is 120. Sometimes it's going to have 3 pairs of electrons, but one of the pairs is not going to be involved in bonding. It's going to be a lone pair. So the shape would still pretty much be the same thing, except that part is missing. So it would just be a fan with one blade missing. So that would be just a bent shape. Let's talk about the third one. And the first option in the third one, that's what if an atom has 4 bonded pairs? So an atom is making 4 bonds. Now, when an atom makes 4 bonds, one example is the CH4 that we did, the sp3 hybridization that we did. So that is tetrahedral. So that means the shape is going to be similar to, there would be one bond coming towards you, one bond going into the page, and let me get one bond going into the page, so it's going to look like this. So all 4 bonds are identical. So there's a bunch of electrons in this bond, electrons over here, and electrons being shared over here. They would all repel each other, and the shape is going to be called tetrahedral. And the angle would be 109.5 degrees. This is the shape that we drew earlier for sp3 hybridization. This is what the atom would look like. This is what the 3-dimensional shape of the molecule would be. One bond on top, one going into the page, one coming towards you. So in total, all the angles would be identical. It's going to look like a pyramid with one bond on top of it. So that's a tetrahedral shape, and the angles are 109.5. Then there would be other versions of this. Version number 2 is, again, you still have 4 pairs of electrons, except that there's going to be one lone pair plus 3 pairs of bonded electrons. Now, in this case, the molecule shape is going to be, for example, ammonia is an example. It's still going to be kind of tetrahedral. So ammonia is NH3. So it's kind of tetrahedral, except that the top is missing. I mean, at the top, there's just a bunch of electrons that are not bonded to anything. So it's exactly the same shape, except there's nothing on the top. There's no atom attached. There are electrons there. So the shape is kind of similar. It's kind of similar. The electrons over here are repelling the bonded electrons over here. They're repelling them, they're repelling them. So it's still 4 pairs of electrons, except there's no atom bonded to the top. So it's just like a pyramid with, I mean, the top is missing. So this is what the shape of an ammonia molecule looks like. So maybe this one, it's so it's like a pyramid. I mean, there are electrons, there are a bunch of electrons at the top, but the top is missing. There's nothing attached to it. So it's going to be, I mean, this one shows the tetrahedral arrangement, except, I mean, you won't count the top. There's nothing there. And also remember, the lone pairs are going to exert a greater repulsion. So the lone pairs are going to push all the other bonds kind of slightly closer together. So the angle would kind of shrink just very slightly to 107 degrees. Previously, the angle was 109.5. They were much further away from each other, not much, by just a small margin. They were slightly further away. But because of the extra repulsion of the lone pair, the angles are now kind of slightly closer together. And then there's a third version of the same thing. That's option number C. Option number C is for the same one. It's 2 bonded pairs. plus 2 lone pairs. Water is an example. Again, it's the total amount of pairs of electrons, that's 4. On two sides, there's a hydrogen atom. But on the other side, there's just a bunch of electrons that are not involved in bonding. So on two sides, there is nothing. I mean, there are electrons there. So the shape is the same, except there's nothing attached on those sides. So the shape of the molecule now is, it's neither pyramidal or neither tetrahedral. What it looks like is this. It's just these two atoms bonded to each other and these two bonded to each other. So it's just a bent shaped. It goes from H to O and O to H. Nothing on that side, on the other side. So this one is a bent, or you can call it a nonlinear shape. And now you've got 2 lone pairs. You've got 2 lone pairs, and those 2 lone pairs are going to exert an even greater repulsion. So the angles, the 2 hydrogen atoms would be even closer together. So the angle shrinks to 104.5 degrees. Is this clear, everyone?
Yes, sir.
So the next one is if you have 5 bond pairs. And that too is going to have a lot of variation. So this is the first of the variations. If you've got, sorry, this is this is 5 bonded pairs. This was, I think, the fourth one that we're doing, 4A. So 5 bonded pairs. Now, if you have 5 bonded pairs around an atom, the bonds would repel each other. So it's going to look like this, that what it's going to look like is that there's going to be a fan in the middle. And the fan, so 3 of the atoms imagine a fan that's so you've got Cl, you've got another Cl, you've got another Cl. So 3 of the atoms are making an angle of 120 degrees, just like in a fan. So it's like a fan, and there's going to be 2 Cl atoms that would be one on the top and one at the bottom. So that's how 5 Cls would be bonded to phosphorus, and they would remain as far away from each other as possible. So imagine there's a fan in the middle and 1 Cl sticking on top of the fan and 1 Cl hanging at the bottom of the fan. So maybe if I can see the PCl5. So I think this one is more realistic. So this shape over here, let me just copy this shape. So this shape over here, it's like a fan in the middle and 1 Cl sticking on top of it and 1 Cl sticking at the bottom of it. So that's how 5 bonded pairs would look like. And the name of the shape in this particular case is going to be called, it's called trigonal bipyramidal. I think by 1 second. Bipyramidal. So that's what 5 bonds would look like. There are other variations of this, but you don't have to go into that much detail. I mean, it's probably never going to be asked. The other variations where there could be a lone pair on one side and no atom attached on one side, and there would be bonds on the other side. So we're going to talk, we're not going to go into that much detail. That's probably never going to be asked. The fifth one is going to be if you have 6 bonded pairs. So if an atom is making 6 bonds. So over here, I didn't tell you the angle over here, the top one, that's 90 degrees. I mean, the top one, the thing that's the seal that's sticking on top and the seal that's hanging at the bottom of the fan, they are making 90-degree angles with the fan. And the angles between the fan or between the seals that are part of the fan, that's 120 degrees. So this one is 6 bonded pairs. Now in 6 bonded pairs, like in an SF6 molecule, you've got 1 fluorine sticking on top. One of the fluorines would be over here on the right, one would be on the left, one would be at the bottom. There's going to be one that would be coming towards you, and there's going to be one that would be going behind the sulfur. So in total, there would be 6 fluorines bonded to it. And that's known as an octahedral shape. All the angles in this case are 90 degrees. So imagine 1 fluorine on top of you, 1 on the right, 1 on the left, 1 below you, 1 in front of you, and 1 behind you. So that's how 6 fluorines are going to be arranged around a sulfur atom if it's making 6 bonds. So you have to remember all these shapes. And in 6 bonds, there's a variation as well. If you've got, so this is option 1. Sometimes you'll have 6 pairs of electrons, but 2 of them would be lone pairs. Plus there would be 4 bonded pairs. Now in that case, xenon with the fluorine, that's there's going to be fluorine at the top, 1 on the right, 1 at the bottom, 1 on the left. And the lone pairs would be, one would be behind xenon and the other one would be in front of xenon. They would be on the z-axis. So if you've got this, so it's the same shape, it's exactly the same shape. One lone pair, for example, if you're the center, there's a fluorine on top, on the right, there's a fluorine, on the left, there's a fluorine, at the bottom, there's a fluorine, and there would be a lone pair that would be right in front of you, and there would be a lone pair that would be just behind you. So that's how 2 lone pairs plus 4 bonded pairs. Now the bonds behind this and in front of this are missing because there is no atom attached on that side. So this would be called just square planar, because just 4 fluorines, 1 pointing upwards, 1 pointing downwards, 1 on the right, 1 on the left. So these are all your shapes that need to be memorized. So just a quick recap. Whenever you see 2 pairs of electrons, 2 pairs of bonded electrons in an atom, that's linear, 180 degrees. Whenever you see 3 bonded pairs, make sure that around the central atom, the shape is going to be fan-shaped, 120 degrees. Sometimes you will still see 3 pairs of electrons, except that 1 of them would be a lone pair and 2 of them would be bonded pairs. So the shape would be kind of similar, except that it's going to be 120 degrees and it's going to be bent because the third part is missing. Similarly, there would be 4 bonded pairs. It's got 2 variations. 4 bonded pairs, that's tetrahedral, 109.5. But if on the 4th side, there's a lone pair, still the same shape. And I forgot to write the name of the shape. This one is called pyramidal or trigonal because the top is missing now. So this is known as trigonal pyramidal. And the angle would slightly shrink because of the extra repulsion exerted by the lone pair. In water, you still have the same shape, 4 pairs of electrons, except that on 2 sides now you've got lone pairs. And 2 sides you've got bonded pairs. Now the angle shrinks even more further. And the shape is now just bent because on 2 sides there's nothing. There's no atom attached. So now it's just an H with an O, and that is then connected to an H. So it's bent nonlinear 104.5 degrees. And then you've got 5 bonds. That's going to be trigonal bipyramidal, and it's going to have 2 sets of angles. The angles between the fans, that's 120 degrees, and the angle that the fan is making with the top one and the bottom one, that's 90 degrees. And then we did 6 bonded pairs. TK, is this all clear?
Yes, sir.
TK, everyone else? Mariam, is this clear? Alicia, is this clear?
Yes, sir.
So now what we're going to do is we've done sigma. Just one second. So we've done sigma and pi bonds, sp3, sp2 hybridization. We've also done the shapes of molecules. Okay, so we're going to revise those by doing questions about them. So first starting with sigma and pi bonds. So I'll just do a couple of questions at the moment. So which feature is present both in ethene and polyethene? So I'll just quickly first tell you what's ethene, what's a polyethene. So ethene is, hopefully everyone knows, it's 2 carbon atoms and it's got a double bond in the center. Polyethene is when monomers join up and the double bond goes away. It's all single bonds. So all of them would be single bonds. Now, first thing, so he's talking about the shape of the molecule. So can anyone tell me how many bonded pairs of electrons are around this carbon atom? You've got bonded electrons over here. I told you, think of the double bond as one thing. So you've got a bunch of electrons over here, you've got a bunch of electrons over here, and a bunch of electrons over here. So around this carbon atom, this one, the central carbon atom, and even if you pick this carbon atom, they're both identical. There's just three pairs of electrons, one on this side, one on this side, and there's a bunch of electrons on this side. So that shape is going to be fan shaped. If you've got 3 bonded pairs, this shape is going to be fan shaped. It's going to be fan shaped. Is this clear?
Yes, sir.
Okay, so Mariam, is this clear?
Yes, sir.
So around this carbon atom, the shape, and the other carbon atom is exactly identical. It's got 3 pairs of electrons around it as well. So we just did discuss this, that whenever you have a carbon atom and it's got 3 pairs of electrons, one on this side, one on this side, one on this side, so it's going to look like a fan, and the angles would be approximately 120 degrees. What about this carbon atom? It's got 4 pairs of bonds. What would be the shape like around this carbon atom? Anyone, what happens if you've got 4 pairs of electrons? If you've got 4 bonds, the shape is tetrahedral and the angle is 109.5. So in this case, it's going to look like this. It's going to be tetrahedral and the angle would be 109.5. So if I draw the first one, it's basically carbon atom, 1 bond coming towards you, and there's going to be 1 bond that would be going into the page. So there's an H. I mean, it's bonded to 2 H atoms. And on this side, there's a carbon atom. So, I mean, if you look at this carbon atom, it's bonded to 2 H. On one side, there's a carbon atom. The other carbon atom is also tetrahedral. So that means the shape would be kind of similar. It's going to be 1 bond coming towards you, 1 going into the page. So it's also bonded to 2 H atoms. So this would be tetrahedral, and this one would also be, both of them would be tetrahedral. So it's probably going to look like this in 3-dimensional. So I wanted to show you, I can't find this. Just wanted to show you a tetrahedral carbon chain. So it's going to look something like this. The first one is tetrahedral, 109.5 degree angles. The second one is also tetrahedral. So that's the actual shape of the molecule. I mean, this is how you simply write it. Like this just shows connectivity, like which atom is bonded to which atom. This also just shows connectivity. It doesn't really show the actual shape of the molecule. So over here, it's fan shaped. So the angle is 109.5 degrees. Whereas over here, it's fan shaped. Fan shaped, they don't have 109.5. They actually have 120 degree angle. Over here, the angle would be 109.5 degrees. So the first option is incorrect. Both of them are not going to have an angle of 109.5. Let's talk about pi covalent bonds. Whenever there's a double bond, that means there's a sigma bond plus there's a pi bond. Over here, there is no double bond, so there is no pi bond. So that is also incorrect. Both of them have sigma bonds because every bond, the first bond that's formed between atoms, that's always a sigma bond. So both of them have sigma bonds, but this one has an additional pi bond. So option C is correct. sp3 hybridization. sp3 hybridization is when carbon is tetrahedral bonded to 4 atoms. So over here, the carbon is sp3 hybridized. When carbon is just bonded to 2 atoms and it's fan shaped, that means it is sp2 hybridized. Okay. So let's continue tomorrow. We'll try and do questions and we'll revise all of this. Okay. Make sure you go over this sigma pi bonds and sp3, sp2 hybridization and the bond angles as well. Okay. Let's continue next time. Okay, everyone.
Allah Hafiz.
Thank you, sir. Allah Hafiz.
Allah Hafiz.
Allah Hafiz.